Hello, our next video is about units. Unit is something that most people don't take much consideration for, but let's say that you found out that I won Powerball, and I sent out a message to everybody in the class, an announcement that said, I know this is an online class, but if everybody shows up to the chemistry lab in Hood River on Monday, I'm going to give everybody 5. And you're thinking to yourself, 5, great. 5 what? Like 5 extra credit points? That would be lame. $5? That would also be lame. But if when you showed up, I said, I'm going to give everybody $5,000 and I hope that pays for your school this year, you'd be like, oh, all right, that's kind of cool. So tell me what was important, the 5 or the thing that follows the 5? The thing that follows the 5 is important. If you ask me, how much money did I win at Powerball? And I said 187, you would say 187 what? The what is the more important part, and the what is what we call a unit. So if we're talking about money, maybe I won $187 million or $187 billion. Obviously, Powerball hasn't gotten that big, or maybe not obviously, but it hasn't. I checked, and it's gotten close to a billion, but certainly not 187 billion. Regardless, the number has some significance, of course, but what's more important is the unit. So every single time somebody takes a measurement or talks about a parameter, and a parameter is something that we measure. So it could be distance, could be time, could be the intensity of a headlamp in lumens, could be whatever you want. The volume of air in a house, because you're going to buy an air conditioner and you want to buy one big enough to cool all of that air. All of these things are parameters. And so when I measure a parameter, like money, I need to put a unit with it. If somebody said, I've got 10,000 in my wallet, you'd be like, wow, how could you even fit $10,000 in your wallet? Is that $1,000 bills? That's still a thick wallet. Well, if I said rubles, you'd be like, ha, that's funny. That's not worth anything. Or drachma, really not worth anything, because that's Greek money that is no longer a thing because of the euro. And I do have some drachma because I was in Greece. Or if somebody said peso, that's much more likely. It's not obviously 10,000. I don't know what the ratio is for dollars to pesos, but it's always been a little obscure. A little inflated when I go from dollars to pesos. So what's the most important thing is what follows the number, and that's the unit. So a unit itself is a standard of measurement. We all know what a dollar is. We all know what a foot is. If somebody says they're 6 feet tall, you have an idea of what that is. If you go to Europe and they say they're 2 meters tall, you're gonna have to think about that, and then you'll probably have to do some math because we're just not used to that. If you go to a basketball court at a grade school, usually there's a 10-foot hoop, which is the regulation hoop, but there's probably also a chance that there's a 9-foot hoop or an 8-foot hoop for little kids. So the standard of measurement is what a unit is, and we all need to agree on that. And so the problem is, for a long time, we didn't agree on that. The foot is based off of the foot of the king. So if I'm in France or if I'm in England, the king's foot's going to be different. So if someone in France says I have 100 foot of rope and I'm going to sell it to this Englishman, the Englishman might show up and be like, that's 80 foot of rope, because the French king might have a short foot compared to the British king. Regardless, it's not standard. And so what we have done, most of the world has done, is they've switched over to the metric system. It happened sometime in the 60s. The system had been around for quite some time, but it became an official unit for the rest of the world in 1960. So we call it the metric system, or the SI system. It's System International des Units. That's the French term for it, because they were the impetus behind the whole movement. And so we didn't do it. Obviously, we didn't do it, since, and we're basically the only country that didn't do it. The other countries that didn't do it are, I don't want to say insignificant, but they're much less influential and much smaller. Myanmar, I think, maybe I can't remember what the other one was, but a very tiny percent of the population uses this. This system that we use called the empirical system. And it would be good if we could change, but the reason we haven't changed yet is simply because of money. So let's just think about this. The United States per square mile has more roads than any other place in the world. We love our cars, we love to drive, we have a lot of land, so we've got a lot of roads. So let's focus on just the gorge area. And so if you're driving from Portland to Hood River, the first exit that you see for Hood River is exit number 62. Exit number 62 means that it's 62 miles from the start of I-84. So I-84 starts where it peels off of I-5 in Portland, right next to the Willamette River. And if you drive 62 miles east, you'll hit the first Hood River exit, plus or minus hundreds of feet, but regardless, about 62 miles. So what would it cost to change all of those signs? Instead of it saying 62 miles, we would have to say about, do this. We have to say about 87 miles. So if I change that sign to say 87 miles, how much does that cost? It's not inexpensive. A decade or so ago, I was on city council in Dallas and I found out that a stop sign cost $600 to install. And that was more than a decade ago. So easily $1,000 to change the signage from miles to kilometers. And it's not just that 62 sign, it's all the signs going up. So now 48 miles from Hood River, 28 miles from Hood River, 60 miles from Hood River, all those signs need to get replaced, plus all the mile markers. So every single mile marker from Portland to Hood River, that 62 mile markers needs to be changed. You're looking at $62,000 right there. Well, actually, it goes both directions. So it's 62 back. So double that, plus all the other signs that say how far you are. So you can quickly ramp this out of control. So it's very expensive. So the United States just said, no, we're just not going to do it. We don't really care. All right, so we're stuck with this aftermath. It would be billions and billions of dollars to get this to switch. So I could see why maybe we didn't do it. Although if we would have done it in 1960, it would be a lot less. There was an industry that never had to go from the empirical to the metric system, and that was the wine industry. Those bottles have been 750 milliliters for the regular size bottle forever because that's what they had, and the bottles were only made in Europe. So if you wanted to make wine in the United States, there weren't any wine bottle producers. So they just made the bottle, they purchased the bottles from Europe. And so they were stuck with the 750 milliliter bottle and they didn't care. They just wrote in ounces on it. But as soon as the metric system happened, they just switched it over to 750. So if you go into the grocery store, go into some winery, you can find a bottle and on it will say 750 milliliters. Unless you're looking at the big bottle, then it's going to say 1500 milliliters or 1.5 liters. Okay, so parameters that we could be measuring length or volume, mass, energy, time, pressure, force. These are all different parameters that we could be measuring. So the metric system works with meters and the empirical system works with feet as the base unit. Volume is liters or gallons, mass is grams or stones. Yeah, stones. Funnier, the other names that you could look up for these are the Gee pound, the Slinch, which is a slug inch, or the blob. Yes, the blob is a unit that has been used for mass. And remember, we talked about mass and weight not being the same thing. Mass is something that is the amount of matter that you've got there, and weight is the amount of gravity on that matter. So they are not the same. So you can look down at the bottom and it says pounds down there because that's pounds is the force of gravity on that object. All right, the stone number or stone unit came from the fact that hundreds of years ago, maybe 1,000+ years ago, when people wanted to know how much say a chicken they were selling, what the mass of that chicken was, they'd put the chicken on a scale, and on the other side of the scale, they put some stones. And when it equaled the weight, if it teeter-tottered to the middle, then they knew that this was a 12 stone chicken. And the problem with that is if the person selling the chicken went to another village, the person with the stones would have different stones. So eventually they had to standardize the stones in an area, and they went with something called slugs, which was chunks of metal. So you can think about a long rod of metal, and then you cut the metal into little coin looking things, and then you distribute those coins, and then those are slugs. And so the slugs would all have the same mass. And so then you can more easily distribute merchandise, and everybody was on the same unit or standard of measurement. Time is seconds for both of those. And we'll talk about how that's can be weird. Oh, we skipped energy. Energy, joules or calories are used for the metric system. Joules is the official unit though, and BTUs, which is British thermal units. You might see that number if you're talking about heating something or cooling something. Usually that's pretty much it for the use of BTUs. We have other units of energy that are even more obscure. Pressure is pascals in the metric system, or PSI, which stands for pounds per square inch. And we get to the last chapter that we're going to take care of in this class, chapter 9. We'll talk about PSI, or pounds per square inch for the pressure. And then force of gravity. And that's where the Newton thing came from, apple falling on his head, whether that happened or not. And then again, pound. And we already talked about these guys. The real reason, the draw of the metric system is it's super easy to convert between different units you've got. So for us, going from inches to feet is probably not a big deal. Probably all pretty good that it's 12 inches. But what about inches in a yard? All right, I got to multiply 12 by 3. I got to remember it's 3 feet per yard. So now I'm at 36. How many inches are in a mile? How many feet are in a mile? 5,280. But do you have that memorized? What if I want to go, instead of from miles to feet to inches, I just want to go straight from miles to inches? I can't do that. I have to have a calculator. I don't know that number off the top of my head, but it's pretty big. It's whatever 5,280 is times 12. So all I need to do for the metric system is I need to move the decimal place around. So if I'm talking about a kilometer, so I'll grab a pen here. Let's say that I'm talking about 5 kilometers. Well, that means 1,000. So really it's 5,000 meters. So I can take the K and get rid of it and substitute in 3 zeros, and 5 kilometers and 5,000 meters are the same thing. So these are units that you would want to commit to memory, from peta all the way down to femto. And so the ones we know are going to be kilo because of kilometers, or kilograms for mass of a person. You're going to know mega most likely because of maybe the megapixels on your camera. Giga, you're probably going to know that because you're buying a computer or some kind of thumb drive and its number of gigabytes enough, like you buy a new Xbox or something like that, it'll be like a 2 terabyte hard drive. And you can see these are going up by thousands. A giga is 1,000 times smaller than a tera, and a mega is 1,000 times smaller than a giga. So that's 6 orders of magnitude. So a tera is 1 billion times bigger than a mega. And then a peta is 10 to the 15th, which is 1,000 times bigger. So what are these things? What are these things? Well, this is 10 to the 3rd, which equals 10 times 10 times 10, and that would equal 1,000. So it's easy to write it like this, because if I'm going to do it 10 to the 15, I got to multiply 10 by 15, or I got to multiply 10 by itself 15 times. That would take a lot to write. So I'm not going to do that. I'm just going to tell you, this is what you do. You multiply 10 15 times by itself, and then you end up with a number with a 1 and 15 zeros, which is what we have right here. And the same thing going the other direction. So a meter, we know about how long a meter is. It's a bit longer than a yard. And then centimeters, there's 100 centimeters in a meter, and a centimeter is about the width of your pinky. And then millimeters are the really small indicators in there, units in there. And so there's 1,000 millimeters in a meter. And so we knew that because it's 0.001, you can see over in the decimal value, or it's 10 to the negative 3. So I'm moving the decimal place 3 spots. Micro, there's lots of reasons you would know micro, nano, that gets a lot of talk in movies and in the news. Pico's even smaller than that, and femto's even smaller than that. So femtos, you could talk about how long a particular process is in a particular chemical reaction. So how long it takes light to do something. You could be measuring that in femtos. Petas, you can be talking about how many times the computer can do a process in petaflops. A flop is how often a transistor is able to turn. So maybe you've got 100 petaflops out of your computer. So how many times it's being able to do a calculation. All right, so I would, if you were in the live class, the face-to-face class, you need to have this committed to memory, and you should probably do that in this class so you can get this a little bit easier. So quick, base first derived. A base unit is, there are 7 base units. All the rest of the units are based on the base units. So length is a base parameter, and area is 2 lengths. So that is a derived unit. So if I want to talk about the distance, let's say it's 10 centimeters. Okay, but let's say I've got a box and this is 12 centimeters, and I want to know what the area is, area of this whole space. So that's just 10 centimeters times 12 centimeters. And so I've got 120 centimeters squared. So that's a derived unit because it's got 2 different length units in it. So a derived unit has at least 2 units, and a base unit is just 1 single unit, something that's being measured. So the 7 base units are right here. They are the meter, they are the kilogram, they're the ampere, the Kelvin, the mole, and the candela. All the other units are based off of these units. So this is a little obscure. The distance of the meter used to be the circumference of the Earth around the equator and then divided up into equal sections. And that was an international unit, but they wanted to make this a universal unit. So now this is going to be silly. Now they've got a container, and on that container, there is a flashlight, and I got a stopwatch, and I turn the light switch on, and the light bursts out of the flashlight. And then I turn the light switch off at 299792458 of a second. So basically 300 billionths of a second. And when I stop it, that distance is 1 meter. So why would they do that? Well, they wanted to be able to send a probe off into space and tell everybody in the universe how long our meter unit was so that they could better find us. Yeah, so if something like Independence Day happens, the movie Independence Day, and aliens come here to steal all our resources, you can blame the French. The next unit is a kilogram. There's actually a kilogram. There is a mass in France underneath what looks like a cake tray. Cake tray is like got a little stand, a little thing here, and then this big piece of glass, and over the top of it, there's a bigger piece of glass, little knob on it, and inside of here, there is the kilogram. Yep, we've got a kilogram. The amp, I missed one here. And then the second. So let's talk about the second for a bit. How long is a second? Well, it used to be some portion of the amount of time it takes to get around our sun, but other aliens wouldn't know anything about that. So what we've done is we've taken an element of a particular isotope of cesium, and this isotope of cesium is radioactive. It's called cesium-133. And the atoms in the cesium-133 decay. And there's a process to the decay, which is very regular. And so let's say this is a detector. So radioactive substances come off of this and run into the detector. And when they do, the detector counts. And when the detector is counted, this number, so a little over 9 billion 100 million, then the clock goes 1 second. So this is why we're calling things an atomic clock. They're counting the number of disintegrations per second. So after 9 billion disintegrations of cesium-133, a second has gone by. You could do this anywhere in the universe. So we've explained that in different manners, and then we again attach that to probes and we send that off into space. The next one that we've got here is the ampere. That's just how we measure. The ampere measures amount of current flow through a wire. We won't really get into it. It's just, again, current flow through a wire. So how much electricity comes through the wire. If I turn on an air conditioner, a lot of electricity is going to go through the wire. If I turn on an LED light bulb, very little electricity is going to go through. So the amount of electrons passing away. Then we have the Kelvin, which is a measure of temperature. And the Kelvin unit is cool because it only goes to 0. There's no negatives to it. And it's about this thing called the triple point of water, which we're not really going to talk about, but it's the point at which water is at a temperature and pressure where it's melting, freezing, condensing, boiling, depositing, and subliming all at the same time. It's weird, but it happens. And it's just a fraction of that point. The mole is just a number. The mole is 6.02 times 10 to the 23rd. It's a number we're going to need for this class. So again, it's just a number. In the same way a dozen is a number, there isn't anything really more to it, except this is a really big number. And the last one is the candela. I don't even know where the candela gets used. I've seen watts for amount of illumination, and I've seen luminas, and the one for computer screens, nips. So I haven't seen this one used, but really it's based on a candle, and it's based on the amount of radiation that a particular candle emits. So yeah, basically the amount of light that an object gives off. So all of those things can be used to make all the rest of the units. As a side note here, a millimeter is the same thing as a centimeter cubed. So there's a milliliter, there's a centimeter cubed in the health care method, and then this is centimeter cubed, how you would write it in a science class. They're all exactly the same thing, there's just different ways to say it. Okay, so this would be a derived unit because there's 3 length units. So I'll give you an example of derived units. We've got the area, volume, speed, acceleration, wave number, which is just a reciprocal unit of how many waves pass a point in a given amount of time. Density is some kind of mass unit divided by a volume unit. Specific volume is a volume divided by mass, sort of the opposite of what density is. So you can see that there are lots of different units put together, but we can really see in some other types of units. And one you might know is the volt. So out of your wall comes 110 volts. It's all of these units put together. So even though it's just a V, it's really all of those things connected up, and then that equals your volt. Or ohms, which is the amount of resistance in a wire, electrical resistance. Again, a whole bunch of units put together to make this volt thing. And yeah, so I just want you to realize that a unit is a standard of measurement. So we've all agreed how big this thing is, and that there's the metric system, which almost the entire world uses except for us and a couple of other countries, and that's called the empirical system. And that there are prefixes for the metric system that we're going to use in this class. And the difference between a base unit and a derived unit, the base unit are the 7 units that everything else is based on. And then I stack those units together to make myself derived units. Like I take a length unit and a time unit, and I put them together to give me a speed unit. Okay, that's it. Thanks.